All right, everybody, thanks for coming in on a Friday. Oceanography on a lazy afternoon. Today we're going to continue talking about wind. Hopefully we'll pretty much finish that up today. In particular, spending a little time talking about local Southern California climate, things like Santa Ana's. We might, at the very end of the day today, start talking about current a little bit. If we don't get it today, we'll do it for much of next week. All right, so where we left off on Wednesday was a discussion of convection as a driving mechanism for winds on the surface of the Earth. The basic idea being that the Earth is heated by the sun most intently near the equator, so we would expect air there to become warm, less dense, and rise up into the atmosphere. We receive the least intense sunlight heating near the poles, South Pole and North Pole, so we should expect air there near the surface to be coldest and most dense and tend to flow out along the surface. And if the Earth wasn't spinning, we might expect in such a system to have a fairly simple wind pattern, that air rises at the equator, moves towards the poles at high altitudes, and then sinks at the poles and returns back to the equator along the surface. And that therefore, in California, living at the surface of the Earth, we would mostly see winds blowing from north to south. We would see northerly winds. But that's not actually what happens because the Earth is spinning. And the spin of the Earth in the northern hemisphere tends to cause flows to be deflected towards the right. So that wind that's trying to blow from the pole towards the equator to return that flow is actually being deflected to the right, in which case it's being deflected into an easterly, a wind that blows from east to west. And so actually, instead of blowing straight from the poles to the equator, the surface winds actually don't make it that far. They get tied up into several wind bands in each hemisphere. And the same happens in the southern hemisphere, but the direction of the deflection is opposite. So flows in the southern hemisphere tend to get bent off towards the left instead of towards the right. All right. Is everybody kind of comfortable with this idea? Flows get directed towards the right in the northern hemisphere and towards the left in the southern hemisphere. We're going to come back to this kind of over and over again for the next couple weeks. So if you get stuck or something, please let your confusion be known. And here's something to make sure you get as confused as possible. So northern hemisphere flows get directed towards the right. Southern hemisphere flows get directed towards the left. Here's a picture of a northern hemisphere storm, a hurricane in the northern Atlantic Ocean, just north of Puerto Rico and Haiti and the Dominican Republic. And here's a southern hemisphere, I guess in this case, cyclone, which is, here's the coast of Australia here. Okay, and northern hemisphere hurricane is spinning counterclockwise. And the southern hemisphere cyclone, which is just it's the same idea as a hurricane, we just call it a cyclone if it's in this particular part of the southern hemisphere. It's just a naming thing. It's flowing clockwise. So if you follow the way things must be bending as they go around the northern hemisphere storm counterclockwise, which direction are the flows bending? They're bending towards the left. What about for the southern hemisphere storm? They're bending towards the right. Okay, which direction is a flow supposed to go in the northern hemisphere? Yeah, there's a problem there, right? So let's figure out what's going on. The critical issue is to remember that these are storms. So we talked about that when air rises, it tends to expand, right? And in the process of expanding, it cools down, and eventually it may lose its capacity to hold on to water vapor, so water vapor will condense out to make clouds, eventually rain. A hurricane is manifestly something that has rain in it, okay? There is air rising in the part of a hurricane you see as clouds. So you have air rising off the surface. That means air has to be coming in from somewhere else to replace it. Right? We don't make a vacuum, at least not a complete one. So we can think of a storm, a hurricane, a typhoon, a cyclone as being examples of low pressure systems at the surface. Okay? Air is rising out of the surface, and it must be getting replaced. So air is being sucked in along the surface of the Earth. Okay? And the air rising is what makes there be clouds and rain. Okay? And the low pressure turns out to be important for understanding why they circulate the way they do. So we can call a hurricane a low pressure system at the Earth's surface. So air elsewhere on the Earth's surface is going to tend to do what in response to being near a low pressure system? There's a little piece of air out there, and because of rising air kind of hoovering away the surface air, what's the air around it going to tend to do? It's going to tend to get sucked in, right? Low pressure system means it's sucking. So we would expect any parcel of air near it, this low pressure system, to be drawn in towards this low pressure. Okay. In the northern hemisphere, what's going to happen to each of those arrows? As the wind tries to get into the middle of this low pressure system to replace all the air that's rising, which way is it going to get deflected? Northern hemisphere. Right. So instead of making it straight into a low pressure system, in fact, these get bent to be not right at the low pressure system, but to the right of the low pressure system. And we've set up a circulation, right? We have an arrow this way, an arrow this way, an arrow this way, an arrow this way, kind of making a circle around this storm. Which direction is the circulation going? Clockwise? Counterclockwise. Okay, so we have in the northern hemisphere a low pressure system, a storm, a hurricane, and air being drawn into it, getting shuttled off to the right, and the net result of that process, the balance that sets up between the low pressure system and air trying to get in and being deflected by Coriolis, is you end up with a counterclockwise circulation. And these arrows, if you follow a little piece of air around, is actually going kind of to the left because it's trying to get into the middle in this case. What if we had a high pressure system? What if air was falling down onto the surface of the Earth and spreading out? So you had extra air coming down to the surface in some place. First of all, what kind of weather would you expect to see under that circumstance? What happens to air when it sinks? It's going to get compressed because the pressure is going up. What happens to air when it compresses? What happens to its temperature? It's going to get warmer. What happens to the ability of air to hold on to water vapor as it warms up? So is it going to lose water vapor to make clouds? No. In fact, the water vapor is more and more happy in the gas phase. It's not going to make clouds at all. So in areas we have air sinking, you might expect it to be kind of warm, perhaps, okay, if it's sinking down from above. And you certainly would expect that air to be relatively dry, okay? And so you wouldn't see clouds there. You wouldn't see like something in a satellite image that was obvious. You would see clear air, okay? But nonetheless, you can still find high pressure areas. So imagine we had a high pressure system off a little ways. If you're a little parcel of air next to the high pressure system, what's going to happen? Which way are you going to want to go? If there's extra air on one side, pressure gradient's going away from it, and so it's going to push all that air away, right? High pressure system's pushing things away. Deflected towards the right in the northern hemisphere. Connect the arrows. The high pressure system goes clockwise. Okay? So the things we see as storms, defined by clouds, where air is rising and there's a low pressure system at the surface, are going to tend to rotate counterclockwise in the northern hemisphere. Areas of clear air, where air is sinking, are going to tend to rotate clockwise. Okay? And the opposite is true in the southern hemisphere. If those arrows were bending towards the left, you would end up with a clockwise circulation around a low pressure system, and you would end up with a counterclockwise rotation around a high pressure system. All right, so let's go back to the picture. So here we have a low pressure system, a very low pressure system in the northern hemisphere. Air is trying to get in, but it's being deflected towards the right. Okay, so it ends up going around that way, making a counterclockwise circulation. In the southern hemisphere, same thing. It's a big low pressure system. Air is trying to get into the middle, but it's being deflected towards the left. And so it ends up having to go around this way, and the storm ends up rotating clockwise. So in fact, Coriolis does make sense for explaining why storms, hurricanes rotate the way they do. You just have to remember the fact that there's lots of clouds and rain there implies that there's rising air, which means air is trying to get into the center along the surface, and the deflection of that air by Coriolis sets up a circulation pattern that's opposite from the way you might originally expect. Okay, so this is an interesting aside. Of course, we're interested in bigger picture issues as well. And so what happens on the global scale is that instead of having air just rising at the equator and sinking at the poles and one circulation cell per hemisphere, we actually end up with 3 because the Earth is spinning. Air still rises at the equator, but in this case it only makes it to about 30 degrees north and south of the equator. At that point, Coriolis has deflected it pretty far. Okay? In the case of the northern hemisphere, it's getting deflected more and more to be a west to east wind. And eventually it kind of runs out of steam and will sink and return to the equator without having actually made it all the way to the poles. So we have a region of sinking air at about 30 degrees. What kind of weather is associated with sinking air? Perhaps warm? Wet or dry? Dry, right? As the air is sinking, it's warming up. It's increasing its ability to hold on to water vapor. It's not going to condense out clouds by any means. And so along about 30 degrees of latitude is in fact where we commonly find things like deserts. The Sahara Desert, okay, the Mojave Desert, the Namib Desert and the Kalahari Deserts, the Atacama Desert. Some of these deserts have other things that are playing a role in controlling the fact that there's deserts there, but it's very common to find them at latitudes of about 30 degrees north and south, consistent with the idea that there's generally air sinking there. Okay, the Earth is spinning. That air doesn't make it all the way from the equator to the North Pole before it sinks. Instead, it sinks at about 30 degrees, creating dry zones. Okay, and then that air returns along the surface towards the equator. In the case of the northern hemisphere, it's trying to go from north to south, but it's getting deflected towards the right. And so it ends up being a wind that goes from east to west, which we would call naming winds after where they come from, we would call it an easterly. And in the case of the winds that occur at the surface between about the equator and 30 degrees, we call them trade winds also. Trade winds are a kind of easterly wind. There's another band between 30 degrees and 60 degrees, which is kind of backwards actually. We have air sinking at the equatorward side and rising at about 60 degrees. Air along the surface is actually moving away from the equator, getting bent towards the right, so it ends up going from west to east, which is a westerly. And then at the pole, we have sinking air right at the pole, deflected to the right in the northern hemisphere, becoming another easterly again. So instead of just having north to south winds everywhere in the northern hemisphere, we have alternating bands. Trade winds relatively close to the equator to about 30 degrees that are easterlies, westerlies between about 30 and 60 degrees, and then easterlies again near the pole. This is a simplification. The little animation I was showing you at the first slide while you guys were all walking in is an actual wind forecast for the Pacific Ocean based on data that have been collected and then a computer model of how the atmosphere is going to circulate. And you can hopefully see some of these same basic ideas, that there are easterlies near the equator, the trade winds. There are westerlies a little bit farther away. And what you can see here is in the band near the equator, most of the arrows are kind of pointing right to left, right? They're easterly winds. If you go a little bit farther away from the equator, away from 30 degrees or so, it's more complicated, but nonetheless, many of the arrows are going from left to right. They're westerlies. Okay, and the same is true up here, sort of off the coast of North America. You can't see the easterlies very well, the polar easterlies very well in this particular figure, but they are there. If we went beyond 75 degrees in particular and paid attention for long enough. Okay, so it really is, you can see this at the surface. A general splitting of the Earth's circulation into easterlies from the equator to about 30 degrees north and south, and westerlies between about 30 and 60 degrees, and then if you get really close to the poles, easterlies again. Okay, so we have 3 convection cells in each hemisphere, about 30 latitudinal degrees wide for each one. We also have regions where there's vertical air movement, air rising at the equator, just like in the no-spin case, because that's where air gets most intensely heated, because the sunlight is most intense there. But it also turns out that we have air rising at about 60 degrees latitude. We have sinking air not just at the poles, like we did in the no-spin case, but also at about 30 degrees. These characteristic sort of 30-degree wide zones of latitude in which there's a prevailing wind direction, either easterly or westerly, we call zones. Those are zonal winds. So the trade winds from the equator to about 30 degrees are the zonal winds closest to the equator. And all of this complication of the simple picture is all ultimately because these flows are trying to go from hot to cold or cold to hot, but are getting deflected by Coriolis, by the fact that the Earth is spinning and the Earth's surface is cool, or is curved, sorry. Okay. So in the vertical sense, rising at the equator, sinking at 30 degrees, rising at 60 degrees, and dropping again at about 90 degrees. And in fact, we have special names for each of these. So the zone between about 0 and 30 degrees, where the surface winds we call the trade winds, the whole convection cell associated with the trade winds we call the Hadley cell. Okay, so the trade winds are the surface part of the Hadley circulation cell. The westerlies between 30 and 60 degrees are the surface part of the Forel cell, which is really weird because it's going backwards. We have air rising where it should be coldest and sinking where it should be warmest. That's kind of weird. And then near the poles, we have the polar cell, which hopefully is relatively self-explanatory. Okay. And the Hadley cell makes sense. We have warm air rising near the equator, sinking as it moves towards the poles. The polar cell makes sense. We have air sinking at the pole and rising as it moves towards the equator. The Forel cell, kind of sandwiched in between, is a little weird, but you can think of it as having to be meshed in between those two big gears. The Hadley cell churning near the equator, the polar cells churning near the poles, and the Forel cell kind of has to go backwards in between to make them work out. This is another picture of the same thing, focusing on the surface winds. Okay, the trade winds blowing from east to west, the westerlies blowing from west to east, and the polar easterlies blowing from east to west again, and also counting the vertical air motion. So we have air rising near the equator, okay, which has to be replaced by stuff flowing in along the surface. So the equator is effectively a low pressure zone. It's an area where air is rising and needs to be replaced by new air coming in. So what kind of weather do we expect to find at the equator? It's going to be dry or wet if air is rising there. Well, a hurricane is a low pressure system. Is a hurricane wet or dry? It's pretty wet. By analogy, okay, wherever you have a low pressure zone in general, you might expect to have relatively wet weather. And in fact, the equator is the wettest place, basically, on the planet, in a broad sense. Areas where air is sinking, like at 30 degrees north and south, it's spreading out along the surface. There's extra air hitting the surface, and so that sinking air is going to tend to be dry. And then again, at about 60 degrees, we have actually another area of rising air, which tends to be relatively humid again. It's also important to realize what these boundaries are about and that they have special properties. In particular, at the equator itself, between the two trade wind bands, the motion of the air is actually as much vertical as anything else, right? We have air coming in, getting heated up, and rising. So the actual surface winds themselves, the horizontal component of the wind, is not terribly strong, and it's not terribly reliable right at the equator itself. In fact, it's common for sailing ships in the old days, when they reach the equator, they just get stuck. The wind stops, it goes away, and they're just drifting in these boats for days, weeks at a time, which doesn't sound like very much fun. You're right at the equator. It's very humid because you're sitting in the ocean, and you're like running out of food, running out of fresh water, and not going anywhere, which doesn't sound like very much fun. So this region is called the doldrums, and hopefully that word is familiar enough to you that it makes some sense. Okay, not much tends to happen there in the form of reliable surface winds that can move a sailing ship from one side to the other. The winds tend to be irregular. This boundary between the two Hadley cells can move a little bit north and south, so it's not like there's never any wind at all, but nonetheless, it can be a tricky place. And in fact, that's going to be true wherever there's vertical wind motion. So at about 30 degrees, where air is predominantly sinking, the winds also can be capricious. They can go and stop and not be consistent. Okay? And those are called the horse latitudes, and they're associated with a jet stream at high altitudes, actually. And then finally, the front between the westerlies and the polar easterlies isn't so important from the point of view of sailing ships. Not a lot of people sail at 60 degrees north and south latitude. But there is a front there, which is actually really important for determining weather patterns. For instance, during the winter, which side of the front we're on and where the front is across the United States is actually really important for figuring out whether there's going to be a snowstorm or a winter storm or nice warm weather. All right. So the basic idea I want you to remember from this is that the Earth's winds are driven by convection, by the fact that the Earth is heated up non-uniformly. It's heated most intensely at the equator, least intensely at the poles. That we know from, for instance, looking at the heat budget of the planet, that heat is being transported from the equator to the poles by both winds and the ocean. And that the fact that the Earth is spinning complicates that convection pattern, divvying up the Earth's winds into 3 bands per hemisphere. Trade winds near the equator, from 0 to about 30 degrees, that blow from east to west. Westerlies that blow from west to east between about 30 and 60 degrees. And then easterlies again, once you get near the poles. Sorry for the ringing. All right, so are there any questions about that? I know I'm putting some of you to sleep. I'm about to do California weather, which hopefully will be a bit more interesting. All right. So what does this mean for us? First of all, does anybody know what the latitude of California is, roughly? Can you figure out which of those wind bands we would be in? Are we going to be in the polar cell? No. Are we going to be in the Ferrel cell, the mid-latitude cell? Who votes for mid-latitude? A few hands. Who votes for Hadley cell, trade winds? About 50-50. Turns out that we're actually usually in the westerlies, actually pretty much always. We're a little bit north of 30 degrees, 34 degrees, 33 degrees, something like that, depending on where exactly you live, of course. And that most often our weather patterns are actually coming from the west. So we're in the westerlies, and most of the United States, except for Hawaii, is actually in the westerly belt. Maybe the very northern part of Alaska also gets polar easterlies, but for the most part, the United States is a westerly belt country. Okay, so how does this overall pattern and our local idiosyncrasies of being a coastal region right up against the Pacific Ocean, how do those things affect our local weather? Well, there are a couple things that are important to remember. One of them, of course, is that our position next to the ocean has a really big effect on our local weather. Okay, we have this thing called the marine layer, or June gloom, which is common during the summer, but actually is a really common weather pattern all year, where we have usually fairly cool, moist air coming off the ocean, filling up the LA basin, keeping our weather more or less constant all the time. Nice, okay, although it might be kind of cloudy in the morning. And in fact, LA's weather is very strongly influenced by our position near the ocean, near the Pacific Ocean. We have what might be called the Mediterranean-like climate, okay, which is common for areas near coasts in our latitude band, a little bit north of 30 degrees or so, okay, which also goes for places like southern Italy or Greece, which would also be considered to have a Mediterranean climate. Okay. So we're at a subtropical latitude. We're not quite in the trade wind belt, but we're not that far from the equator. We're right up against the ocean. The ocean is usually colder than the land. Okay, we're reasonably close to the equator. We get pretty intense heating. It's usually sunny and clear here. The land tends to be relatively warm, but the ocean is fairly cool. Air in contact with that ocean is going to tend to cool off and sink. Okay, and then that partly means it's clear most of the year, and that also partly comes just because we're close to 30 degrees north. We're in this area between the trade winds and the westerlies where air tends to sink, even if we're on the westerly side of it. The coastline has an effect, however, because winds coming off the ocean have been in contact with water for a long time and tend to have evaporated some of that ocean water, and so they come onto land with fairly high humidity most of the time. Okay? And the surface ocean has a really high thermal inertia. It takes lots of heat energy to warm up the ocean. Its temperature doesn't change very much from day to night. It doesn't change very much from summer to winter. And so any air that's blowing over that surface tends to regularize its temperature. And since we're near that ocean body, we get the benefit of that fairly small change in temperature from day to night and from winter to fall to winter to spring. However, particularly during the winter, things get a little more exciting. Okay? In particular, the temperature difference between the poles and the equator tends to be most intense during winter because this whole area near the poles just becomes totally dark and really gets cold. Okay? And so the cold area kind of advances towards the equator, and the difference between the equator and 60 or 70 degrees is much more intense because 60 or 70 degrees is completely dark during the winter and very cold. And so the convection in the northern hemisphere is compressed into a smaller part of the planet, that same temperature gradient, and so the flows kind of get faster and faster and faster because all this energy transport is happening over a shorter distance. So this speeds up, for instance, the winds flowing along the boundaries between the cells, and it can cause undulations in those cells that send moisture our way, even though we usually don't get it because we're kind of near this area of sinking air. So winter is the exciting time for the most part in California. Okay. And we have local things that go on that make a really big difference to our local weather pattern because we're right on the ocean. And two of these phenomena are worth singling out. One of them is what's called the sea breeze. And this is actually pretty common, not just in California. It doesn't require an ocean. It's very common for communities on the shore of a lake, for instance. Any relatively large body of water can set up a sea breeze or a lake breeze, or even perhaps a river breeze. And the basic idea here is imagine that we have a nice sunny day, and sun's falling down on the land surface and it's falling down on the ocean surface. But the land is going to tend to heat up much faster. First of all, rocks have a much lower heat capacity than water. So the same amount of heat is going to raise the temperature of the land much more than the ocean. And also that heat energy on land, sunlight only penetrates, millimeters or through the trees or barely to the ground. So all the heating happens right at the surface where that heat can go into the air. In the ocean, sunlight heat is absorbed over 100 meters or so of water, so it has to heat up a lot of water before it starts changing its temperature very much. So for that reason, you might expect during the day, particularly towards the afternoon, the temperature right at the land surface is going up. It's higher than it is over the ocean because it's changing faster and sunlight's falling on everything. So the air in contact with the land surface, warming up, it's going to tend to expand. It's going to become less dense. It's going to tend to rise. Air over the ocean surface temperature doesn't really change very much. It doesn't really even know that it's daytime, okay, from the point of view of its temperature. So it's staying the same. So it's getting surpassed in its temperature by the land air, and therefore it's becoming more dense than the land air. So land air rises and gets replaced by denser ocean air flowing onto the land. So if you're standing at the beach on a typical summer day, and you're flying a kite or you're going kiteboarding, which always looks like fun but kind of scary, you should expect that the wind is going to be blowing your kite inland. Okay, and that's in fact usually what's seen. Okay. This more dense air over the ocean that isn't getting warmed up very much during the day is flowing in to displace the less dense air on land that's getting heated up and rising. Okay. If there was going to be rain here, where would the rain be happening? If you were going to make clouds, where would the clouds be? Why over the ocean? Okay, that's good, yes. So imagine that if the ocean's cold enough, then air kind of flowing over it might start to condense just because it's getting cold, chilled by the water. And so you might expect to see condensation occurring right along the surface of the ocean. And in fact, that's where a marine layer comes from. So yeah, that's one way you can get clouds. Usually we don't get rain from those because it's right at the ocean itself and it's not usually very thick, but you can get a little bit of sprinkle that way. You can certainly get clouds that way. We'll talk about that in a minute. Where else might you get clouds and rain? You tend to get condensation where air is being cooled, and one way you can cool air is by putting it next to something that's cold. Another way that you can cool air is by having it expand. You expand air by making it rise. So where is the rising air here? Yeah, it's over the land. So you could get clouds right along the surface of the ocean, and you do. And you can also get clouds inland where the air is starting to rise. If it has enough water and it's getting heated intensely enough that it rises far enough, it might also start to condense. So there are actually a couple places in this picture where you could get clouds. Okay, now the sun goes down, and the roles get kind of reversed. Again, the ocean doesn't warm up or cool down very quickly. The air in contact with the ocean surface doesn't really care whether it's day or night. Its temperature is roughly the same. But the land is going to tend to cool off pretty quickly. Low heat capacity, not very much of it got warmed up during the daytime, and a lot of that heat went into the air. And so by midnight or sometime early in the wee hours of the morning, you might expect that the land surface is actually colder than the ocean surface nearby. And so air over that land surface is going to tend to get chilled. It's going to tend to become more dense, and it will actually flow out and displace the water over the ocean. So the direction of the wind here reversed from daytime to nighttime. Okay? It was an onshore breeze during the day, becomes an offshore breeze at night. And this can happen not just day to night, but you could also imagine something similar happening winter to summer, right? If you have really intense sunlight during the summer or more sunlight, the land's going to tend to respond to that faster. And as everything cools off, you might expect the land to cool off a little faster. So you can imagine this occurring not just on a daily cycle, but also on an annual cycle or a week-to-week cycle, depending on what the source of heating and cooling is. Okay. So, as we were led, very nicely, we could also imagine that, in particular, if we have cold water offshore for some reason, that air blowing over that very cold water might just get chilled by being in contact with something that's cold. Even if it's not rising, you can still cool off air if it's next to something that's cold. And in the case of the ocean in California, it turns out that the water offshore tends to be pretty cold for various reasons that we'll get to when we start talking about ocean circulation. Cold enough, in fact, that air flowing across it can start to condense. Okay? So if we have cold water offshore and warm air from somewhere else is flowing over it that has lots of water vapor dissolved in it, or water vapor carried in it in the gas phase, you may actually not be able to hold on to it once it comes into contact with that cold water, and you may make a layer of clouds right near the surface. We could call that a fog, or we could call it a marine layer. They're kind of related ideas. Okay? And if we have this cold air right at the surface of the ocean, being cold, it's going to tend to be relatively dense. So if there's not a lot of externally imposed strong winds, okay, you might expect that this cold air, just because it's cold and dense, is actually going to tend to spread out over low-lying areas of land. Okay, it might get overruled if there's a strong land breeze, for instance, but if there's not a strong land breeze, then it might win out, and that cold air might be able to surge inland. Okay? And this is what typically happens. This is a very common, probably the most common weather pattern for the Los Angeles area, and in fact the entire coast of California, that the cold water offshore kind of dominates the local weather pattern, makes relatively dense, sometimes foggy air that can then roll inland over low-lying areas and give us a marine layer, okay, or June gloom. And of course, once the sun comes up, its days are numbered because, of course, the land is going to start to warm up relatively quickly, and the air warming up also under sunshine is going to tend to be able to take that water vapor back out of the clouds and become clear again. So the fate of these marine layers is typically that they kind of go away, particularly over land, once the sun rises. Okay, so we can see this in the case of our science quad at UCLA. We're pretty close to the ocean. Our elevation is only 100 or so meters above sea level, so we get marine layers in the morning pretty commonly. So it starts out socked in at like 7 in the morning. Once the sun comes up, the land surface starts to warm up, and by mid-afternoon, it's a nice clear day with blue skies. But then as the sunlight goes away again, the land surface isn't as hot anymore, and so the marine layer starts to take over and rolls right back in. And this is a really common weather pattern, particularly during sort of late spring, early summer, when the land is just starting to warm up and the ocean is still nice and cold. Okay, and it can make this really dense air that flows out over the land. Okay. So that's probably the most common nice weather pattern in Southern California. Maybe a little foggy and a little cold in the morning, but then by the midday it's kind of nice and clear but not too hot because of that ocean influence. However, we're pretty close to 30 degrees north. Okay, and 30 degrees north and 30 degrees south is an area of sinking air, and that's the part of the world where deserts, the most severe hot deserts, tend to occur. And we're pretty close to being a desert. And in particular, if you remove the ocean influence, okay, for whatever reason we're getting air not from the ocean, but from inland, we pretty much turn into a desert, at least temporarily. Okay, and one particularly graphic example of this occurs during Santa Ana events, or during Santa Ana winds, which are one of a family of winds where air is blowing in the interior, okay, over land, and in particular in places where wind is blowing from an area of high elevation to an area of low elevation. So in the case of Canada or Colorado, okay, you have the high Rocky Mountains, and you have low plains that are right near them. And in those places, the air might blow over the mountains and down into the plains. And you get Chinook winds, which is a word that I think means snow eater. So they typically occur during the winter. They're relatively warm. The snow just goes away. In the Alps, you get foehn winds. In France, the Mistral. And in Southern California, we get Santa Anas. So let's look at those in a little bit more detail. So this is the basic set. We can get Santa Anas actually any time of the year, but it's pretty typical to have them during kind of fall, winter. And this is the typical weather pattern that causes them. High pressure area somewhere over the interior of the western United States. Okay, this is kind of a cartoon, but the basic idea is there. We have extra air, sinking air somewhere over the United States. Air is moving out, tends to get bent towards the right, so you end up with a clockwise flow. Being on the outskirts of that high pressure system, we're going to tend to get air that's blowing out of it. Okay. And in LA in particular, in Orange County, okay, we're right near the coast. Our elevation is very low. But if you go inland, we have all these really high plains, like the Mojave, okay, like the Poway and the Peninsular Ranges near San Diego, where the wind is actually blowing across land surface that's a kilometer or so above sea level. It's actually pretty high up. And in order to get into LA, if it's being pushed by a high pressure system, it has to go through a mountain pass, like the Cajon Pass, and then down into the valleys. So a couple things happen during this process. For one thing, in those passes where the wind is getting funneled through, because it doesn't want to go up and over, it just wants to find the shortest way to get away from that high pressure system, you can get really strong winds. Okay? It's trying to go through the window, all this air, and so it rushes through. So you can get hurricane force winds. The other thing that happens is we have air that's at high elevation, high altitude, because it's over land that's pretty high, and then it's coming down near to sea level. So air is sinking, okay, and it's being forced to sink by the land surface. And of course, as air sinks, the pressure on it increases, it gets compressed, and it warms up. Okay? So the air might be normal or cold even in its temperature in the high desert, but by the time it drops a kilometer or so into the LA basin, it warms up by something like 10 degrees Celsius per kilometer of drop. So it tends to be really hot, okay? And it's just been over the desert, so it doesn't have very much water in it to begin with. It doesn't have very much water vapor. And yet it's dropping even further and warming up even more. So its ability to hold on to water vapor is increasing, even though there's no source of extra water vapor going into it. So that air becomes hot, and it becomes really, really dry, okay, because it's warming up as it goes downhill. And so by the time that wind makes it into the LA area, it is hot, it is very dry, and of course, it's carrying some karma with it, because most of the time we have winds blowing off the ocean, so all the exhaust from Westwood and Santa Monica very conveniently gets blown into San Bernardino, and we don't have to worry about it anymore. Okay? But during a Santa Ana, it goes the other way. So everybody's tailpipe in San Bernardino and Riverside gets blown right over our heads. Okay? So not only is it hot, dry, and itchy, it's also stinky, okay, and not very good for us health-wise either. So Santa Ana days are kind of bad mood days for a lot of people. And of course, if you're trying to fight a fire, it's really bad news, because not only is the air dry, but up in the mountains where the forests are, it tends to be very fast. Okay? So often the helicopters that carry water, the planes that drop water, can't even fly just because the winds are so strong. Okay? So here's actually a picture from a few years ago, I think. It may even be 10 years old now. The Santa Ana event. And I showed you some movies where we are looking at wind patterns across the surface of the Pacific Ocean. We can actually make similar maps for closer in areas. And this is during a Santa Ana event with us in LA being right here. Here's Santa Catalina Island. In this case, the wind is blowing offshore. It's getting hot, and it's blowing very quickly. And in fact, it's being pushed so hard, it's going hundreds of miles out to sea. And since these are commonly times during which forest fires start or get out of control, it's pretty common to see, like on the NASA websites, pictures like this during the fall. This is actually from the Porter Ranch fire last October, not this October. That was a fire up in the western San Gabriel Mountains, or just north of the San Fernando Valley. We have a Santa Ana event. So these fires are here, they're making smoke, and that smoke is getting blown right offshore. And yeah, I remember that day. That was, a smelly day. It smelled like, at UCLA, it smelled like there was a campfire like right up the hill or something. Somebody was smoking hams or something. Okay. Any questions then about Los Angeles, our kind of precarious position between being a nice, calm, clement Mediterranean climate, and then from time to time our desert heritage, raises its head, and we become kind of a nasty, itchy place to be for a few days. By the way, there is a note on this, but I didn't make it a big deal about it. It's kind of bad news for people on land during a Santa Ana day, but if you're like a microorganism trying to make your living out here, we talked about how organisms tend to be limited in their ability to grow by availability of things like nitrogen and phosphorus that comes from decaying or oxidized organic material. Here's some oxidized organic material that's very conveniently being blown right over their heads. So one idea is, in fact, during Santa Ana events, the critters living on the surface of the ocean are really happy, okay, because all this wonderful stuff is blowing in that they can use to grow on. It also turns out that these winds, we'll learn this in the next couple of lectures, they tend to drag the surface of the ocean along with them. Okay, so the offshore wind tends to create an offshore current that dredges up deep water to replace the water that's being blown offshore. So you actually can bring up nutrients from the deep part of the ocean at the same time. All right, so we'll come back on Monday and we'll start talking about currents.